Hi friends, welcome back to this module of F block element. Again in this module we are going to learn about oxidation states of lanthanide, but this time we are going to talk about element gadolinium to lutetium, that is atomic number 64 to 71. So first we all have to consider the element which are included from gadolinium to lutetium, and then we will talk about the outer electronic configuration. Now if you will see, in their elementary state, all these elements in their pre-penultimate shell is consisting of 4f orbital. But in the penultimate shell, these all are consisting of 5d orbital, and in case of valence shell, they all are consisting of 6s orbital. As we know that, according to rule of extra stability, first element lanthanum, central element gadolinium, and last element lutetium do not change their electronic configuration in the observed state, because they possess one electron into the 5d orbital, but for rest of the lanthanide the d electron gets shifted from d to f. So element gadolinium and lutetium are not going to change their configuration, and for gadolinium it will be 6s25d1 4f7, which is highly stable, and for lutetium it is 6s25d1 4f14, which is again stable. But for rest of the element there is no change in the 6s electron, so all 6s orbital is consisting of 2 electrons. Now all 5d electron has shifted to 4f, so all 5d electron will be taken as what 0, and there will be increase in 1 electron in the 4f subshell. So from terbium to ytterbium, if you will see, there is increase in 1 electron. Now we all know that the lanthanide shows oxidation state of +3, which is considered to be the common oxidation state. So for gadolinium it is +3. Similarly for the rest of the lanthanide also, they all have common oxidation state of +3. But this +3 oxidation state, when we are writing metal configuration in tri-positive oxidation state, then always remember the +3 oxidation state is achieved by loss of 1 electron from 5d orbital, that is from the penultimate shell, and 2 electron from the 6s orbital. So if I am removing 2 electrons from the 6s orbital and 1 electron from the 5d orbital of gadolinium, so it will become 4f7. Similarly, in case of the other element also, we have to remove 2 electron from 6s, so all 6s will become 0. Since 5d is consisting of 0 electrons, so there will be decrease in 1 electron into 4f orbital. So terbium will become 4f8, dysprosium will become 4f9, holmium will become 4f10, erbium will become 4f11, thulium will become 4f12, and ytterbium will become 4f13, and lutetium will remain as 4f14. Now out of all this configuration, if you will see for gadolinium +3 and lutetium +3, then their configuration is 4f7 and 4f14. I mean to say, gadolinium and lutetium 3+ ion have extra stability. This is due to the half filled f orbital and completely filled f orbital. Along with this +3 oxidation state, if you will see, ytterbium is exhibiting +2 oxidation state, and also in +2 oxidation state it is having configuration of 4f7, which is actually highly stable. Along with the ytterbium, if you will see, there are 2 elements, that is terbium and holmium, which are exhibiting +4 oxidation state. So when we are writing configuration in tetra-positive oxidation state, so there is loss of 2 electron from 6s and 2 electron from the 4f orbital. So terbium 4+ will have configuration of 4f7, and again +4 oxidation state is what highly stable. Now if you will see, ytterbium 2+ and terbium 4+ ion have extra stability. Now this extra stability is due to the half filled f orbital and completely filled f orbital. Along with it, if you will see, there are certain elements which are having common oxidation state of +3 as well as of +2. For example, europium 63, and the configuration is, if you will see, 4f7 5d0 6s2. If I am writing europium 2+, so there will be loss of 2 electron from the 6s orbital, and it will become 4f7. Now europium 2+ is highly stable since it is consisting of half filled f orbital. Second element, if you will see, the ytterbium, which is 70. Now ytterbium is having configuration of 4f14 5d0 6s2. Now ytterbium 2 plus means loss of 2 electron from this 6s orbital, and that's why ytterbium 2 plus will have 4f14. Again, there is stability of this ion. It is due to the completely filled orbital. Along with it, the element which are actually exhibiting +3 as well as +4 oxidation state. So the very first in the series is what? Cerium, which is first lanthanide. Cerium is having configuration of 4f2 5d06s2. If I am writing cerium 4 plus, so there will be loss of 4 electron, that is 2 from 6s orbital and 2 from 4f orbital. So it will become 4f0, means we are getting vacant orbital, and that's why it is what? Highly stable. Now the next element, if you will see, ytterbium, that comes after gadolinium, and the configuration is what? 4f9 5d06s2. So if I am saying terbium 4 plus, so loss of 2 electron from 6s and 2 electron from 4f, so it will become 4f7, and because of the half filled orbital, again terbium 4 plus is what? Highly stable. I mean to say that the ions which are in the lower oxidation state, for example samarium 2 plus, europium 2 plus, ytterbium 2 plus, these all are acting as good reducing agent, but the ions which are in the higher oxidation state, they act as good oxidizing agent. For example, cerium 4 plus and terbium 4 plus. And also, if you will see, element shows oxidation state of 2 plus and 4 plus, even though they do not contain of extra stable configuration. For example, if you will see, praseodymium 4 plus is 4f1, neodymium 2 plus is 4f4, samarium 2 plus is 4f6, dysprosium 4 plus is 4f8. That's all in this model. Thank you very much.